And good afternoon. Thank you for joining us for this virtual session that we have for the coming up 45 minutes. We have Randy Shoup joining us to talk about agility and architecture together, enabling a fast flow of change. I'm looking forward to this one. Randy, please take it away.
Great. Hi, everybody. Like Stacy said, I'm Randy Shoup, and today I want to talk to you about agility and architecture together. Very briefly on my background. Over the last couple of decades, I've been an engineering leader at eBay, at Google, at Stitch Fix, and at WeWork. And then a bunch of these lessons that I learned from all these places are going to, kind of figure into the talk as we go forward. So the general idea here is that, high-performing organizations like the ones I've mentioned and maybe other ones that we've admired need both an agile approach to software development and at the same time a solid architecture. And I think there's kind of an idea in the industry that there's a little bit of a conflict between agility and architecture. And I guess I want to say that I don't think there's a conflict at all. And in fact, agility and architecture are sort of self-reinforcing, that we can't really have good architecture unless we have agile processes, and we aren't able to move in an agile way without a good solid architecture under our feet. And the insight behind that is that, both agility and architecture enable us to do constant change. They enable us to take incremental iterative steps toward making the software better, and it also enable us to get fast feedback. So I want to start with two architecture stories and sort of to illustrate some of the points, and then we're going to get into some more details going forward. So the first architecture story I want to tell is the eBay one. So eBay, depending on how you count, is on its fifth complete rewrite of its infrastructure. So it started famously just about 27 years ago as a monolithic Perl application. So the founder, Pierre Omidyar, was playing around with this new cool thing at the time called the web. Maybe you've heard of it. And he built the thing that became eBay, over a 3-day weekend in Labor Day in 1995. The next iteration of eBay was called V2, very cleverly. It was a monolithic C++ monstrosity in an ISAPI DLL. At its worst, it grew to 3.4 million lines of code in that DLL, and they were actually hitting compiler limits on the number of methods per class, which I'm embarrassed to say I know that the Microsoft compiler at the time could only hold 16K methods per class, and they were actually hitting that limit. So that was a pretty challenging architecture and very difficult to be agile in. During the time about 2002 to 2006, they migrated to what they called V3. And I wouldn't really call that microservices yet, but maybe mini applications. So there was a Java application that was for each part of the site. So, one for buying, one for selling, one for search, one for payments, etc. 200 of those, and together that made up the eBay site. And those applications lived over a sort of sea of shared databases. And then there have been two subsequent iterations, mostly in Java, and then Java and Node since that time. So eBay's architecture has evolved over time, and each time it's been an attempt to make things smaller and make it easier to be more agile. So Amazon has gone through a similar evolution and almost a similar timescale. So Amazon also started in the 1995 timeframe. Amazon's initial, attempt at their architecture was a monolithic Perl and Mason front end over a back end that was written in C. It was a 4 GB application that was in a 4 GB address space. So like the application didn't even fit all in main memory. It's 32-bit machines. They were regularly breaking the GNU linker trying to build their application, so that was pretty unpleasant. And then the application was so, let's call it, effective at leaking memory, they were needing to restart the application every 100 to 200 requests. So that was pretty unpleasant. And then again, from an agile perspective, it was so difficult to work in this environment that Amazon was only releasing once per quarter. So in the time frame 2001 to 2005, Amazon completely retooled their architecture and moved to services, mostly written in the modern languages of the time, C++ and Java. And then from an edict directly from Jeff Bezos, there was no shared databases. So, every interaction between services was through the published service interface. And then there have been a bunch of iterations to Amazon's architecture since that time. But the thing to mention is that basically right after they finished this migration, they started, AWS, Amazon Web Services, and then they started their sort of successive takeover of the world's online retail. So if anybody thinks that architecture doesn't matter, like this is a great story to tell. Okay, so a couple of lessons to learn from here. None of these companies started with what we would call microservices, but past a certain scale, almost every company that I know has ended up migrating to something that we would call microservices now. And we're going to try to understand why that's true, through the rest of this talk. But the other lesson to learn is, as I like to say, if you don't end up regretting your early technology decisions, you probably over-engineered. There may well have been another company, in 1995 that instead of meeting their customer needs and working within a monolith, instead they, built a distributed system for 5 or 10 years in the future. And there's a reason why we've never heard of that company. So the structure of the talk is like this. First, I want to talk about how agility and architecture can help us to drive business and customer value. So that's building the right thing. Then I want to talk about enabling a fast flow of change. So that's building the thing right. And then I want to talk about long-term evolution, like how we can, as we've seen in the examples of eBay and Amazon, how we can continue to evolve the architecture and our agile processes over time. So let's start by talking about business and customer value. So I want to talk about defining the problem that we want to solve. I want to talk about iterative development practices. And then I want to talk about how we build features and architecture ilities effectively. So the first, maybe thing I'd like you to take away is these 7 words. It's what problem are we trying to solve? In almost every instance of my, career, I'm using these 7 words all the time. It's super important for us to really understand exactly what the customer and business problem is. Otherwise, what architecture are we even building? And what do we have our agile processes even agiling for? So why do we want to do this from an engineering perspective? I love this quote from Charles Kettering that a problem well stated is a problem half solved. If we're very clear on what the problem statement is, it makes it a lot easier for us to understand what the solution is and gives us a leg up on getting there. The other super important idea here comes from Mary and Tom Poppendick's excellent book from 2003, Lean Software Development. And that is building the wrong thing is the biggest waste in software development. They outline lots of waste, 7 different wastes in software development. But the most important waste is, building the wrong thing. So now let's talk a little bit more about how we build the thing right from a process perspective. So, traditional organizations do this. Like if we have 5 people, or maybe we have 5 teams and we have more than 5 things to do, we give, the top priority thing to the first team, the next priority thing to the second team, et cetera, or within a team. But I think we can do better than this. It's more important that we actually limit work in progress so that we're able to make faster improvements on the stuff that we're working on. So rather than, working on a whole bunch of things in parallel and only getting them all done at the end, let's work on a smaller number of things, maybe double up people on those individual things and get those things done earlier. But I think we can do better than this. We can, if we release individual iterative units of work over time, we're actually able to produce more value as we go along, and we're actually able to learn more quickly over time and produce better customer and business value. And then it also makes us resistant to this. So I can't tell you how many times, when I was in that old style of work, we'd be working maybe for weeks and months, and then we'd get a change of priorities sometime before we were actually done. And all of that work that we'd done before we released was a complete waste. So by being iterative and by working on smaller units of work at once, we're able to be resistant to this. So what did we learn here? If we do it this way, we're going to deliver the highest priority features first, like we're not going to treat priority 1 and priority 5 the same. We're going to deliver incremental value along the way, which has a lot more value. We're going to deliver value despite changing priorities. So at any point we can, stop and pause and do something else, and we've already delivered a bunch of incremental value. And then finally, and maybe most importantly, it enables us to experiment and learn over time. And we can continue doing things if the results are positive, and we can abandon those things if the results are negative or neutral. And so the critical point about that experimentation comes from Ronnie Kohavi, who used to run experimentation at Microsoft. Then he ran it at maybe Amazon, and then now I think he's at Airbnb. but he has these incredibly striking results. So in a bunch of stuff that Microsoft has built, when they do A/B tests, they discover that 1/3 of the features that they decided to build actually are positive and statistically significant. 1/3 of the features are flat. In other words, there's no statistical difference at all. It didn't make a difference in the metrics. And 1/3 of the features are actually negative. So it turns out that by building things in an incremental way and experimenting in like a robust scientific way, it allows us to figure out which of those third are the good ones and we should keep doing, and which of the 2/3 are the ones that don't make a difference or are bad and we should stop doing those things. So, this is where agile practices really come into play. And the last thing I want to say about this section is sort of from an architecture perspective. We think about features as the things that are visible to the user, but these kind of architecture ilities, the sort of architecture foundations, are also critical features. And to me, I call these the priority 0 features. And you might have a different list, but it definitely includes things like performance and scalability and correctness and security. So all these things are critical features that are part of providing the customer and business value that we're trying to do here. Okay, so we talked about how agility and architecture together can provide business and customer value. Now I want to spend a lot of time talking about how they can drive a fast, sustainable flow of change. And so here what I mean is building the thing right. So here I want to talk about empowered teams. I want to talk about a modular architecture. I want to talk about taking small steps. And I want to talk about making sure that we prioritize getting fast feedback for ourselves. So traditional organizations, like when I started in the industry, and maybe some of you work in organizations that are still like this, is, we'd have a bunch of people that would come up with the idea, and maybe we would call them product or business analysts. Then we would have, the well-paid typists, like a lot of us are, where we would, type furiously into our editors and develop the software. Then we would throw that software over the wall to some quality people, and they would try to see if we did a good job at building that software. And then finally, we would throw that over the wall to some people who would operate the software in the real world. Well, what we've learned over decades is that this is not a very good way to build software. Instead, what we want to do is we want to align teams around a particular customer and business value problem, and we want to put all those skill sets together in the same team. So to borrow a phrase from the Team Topologies book, which I strongly recommend, we talk about stream-aligned teams, so teams that are aligned around a particular customer or business problem. And typically they're building a single service or application or a set of related services or applications, and they have clear goals and metrics, back to the earlier points we were talking about, clear goals and metrics that matter to customers that they're trying to drive. And in order for that to work, those stream-aligned teams need to be independent of each other. They need to be able to have all the required skills and capabilities within the team to solve whatever customer or business problem that they're assigned to do. They need to be able to design, develop, deploy, and operate their services independently of other teams. And we want to make sure that those teams own their services and applications end to end, all the way from the idea all the way through to potentially deprecating and removing it at the end of its life cycle. And the way I like to think about it as a sort of engineering leader perspective is I want to organize my organization such that about 80% of the team's work should be within their boundary. In other words, 80% of the work that a team is doing does not involve, fine-grained coordination with other teams. It can never be 100% because almost anything that we do strategically at the company, requires crossing a bunch of team boundaries. But we want the vast majority, sort of 80-20 rule of what the team's work to be within that boundary, so that the teams can move quickly and get fast feedback. And from a kind of overall organizational perspective, when we have teams that look like that, the overall organization is going to look like this, where we have individual teams that each are responsible for a particular domain of our overall problem. They have all the skill sets within that team boundary to do the work that they need to do. They have the idea generation, they have development and quality and operations. And then that allows us to have a very fast feedback loop and work independently of each other, so the teams can continue to provide business value really, really quickly. So now let's get into, how does architecture help to drive fast flow of change? So the first idea here is building services in a modular way. And this is sort of the architecture equivalent of the team structure that I was talking about just a moment ago, right? So we want the service boundaries of the services that we build to match the problem domain. We want them to, if we look at a service, we want to be able to see that that service has some direct relation to the product domain, that there's sort of a one-to-one relationship between a domain problem and a service that solves it. And those, from an architecture perspective, those service boundaries are encapsulating both business logic and data. And sort of as in the Amazon example, all of the outsiders have with that service are through the publish service interface. That service interface is hiding the internal implementation details behind that service. And critically, there are no backdoors. There's no way for somebody, kind of go behind the service's back and interact directly with its data storage or whatever. And then from an architecture perspective, those under a bunch of those architecture ilities, right? So they're a fault isolation boundary. They're an opportunity for us to do performance optimization within that service boundary. And then critically in the modern world, they're also a security boundary. So next, let's talk about what happens within one of those services. So, the way I like to think about it is we really want to have orthogonal domain logic. What do I mean by that? I mean that the domain logic within the service is ideally implemented in a stateless way. It's implemented in a pure function. That domain logic matches the domain problem really directly. And if we do it this way, and we keep the rest of the non-domain logic, the sort of IO related things, the inputs and the outputs and all the side effects and so on, if we keep those separate, then it turns out that this stateless domain logic in the center is pretty deterministic, and it's also testable in isolation. We're going to see why that matters in just a moment. And also, interestingly, if we keep the domain logic very pure from the perspective of the domain, that tends to be more robust to change over time. So since the domain changes a lot more slowly a lot of times than our technology. We want to make sure from a performance perspective that we're implementing that domain logic in a very kind of straightforward way. I like to think of it as, straight line processing. So it's straightforward within that boundary. It's synchronous, minimal branching, just very straightforward and clean. And then again, as I mentioned, we want to make sure that domain logic is explicitly separated from the IO. So, words that we have for this nowadays are things like hexagonal architecture, the ports and adapters pattern, or the functional folks like to talk about this as, functional core and imperative shell. So next I want to talk about, we were talking about services. I think of that as kind of like making vertical boundaries within our architecture. Now I want to talk about making horizontal boundaries. So the high-performing organizations that I've worked at tend to have a kind of layered approach to services, or at least multiple levels of services. So we'll have those stream-aligned services at the top, and then we'll have common services that provide and abstract out widely used capabilities that are used across those stream-aligned teams. And then over time, we'll see that a service ecosystem builds up, that services call other services, which in turn call other services. And then it's really more of a graph, more of a computational graph. So, A calls B, which calls C and D, et cetera. And these services are going to grow and evolve over time. So over time, we're going to find more opportunities for us to factor out common libraries and common services and share them among a bunch of different teams and applications. The other kind of related horizontal idea is developing a sort of common infrastructure platform. So the highest performing organizations that I know all provide a common shared infrastructure, whether that's cloud or on-prem or whatever. They provide standard development frameworks that make it easy for teams to develop in the common ways. Common sort of frameworks. They provide capabilities for the development experience, like building and testing and CI/CD pipelines, et cetera. And Netflix and Google are really known for providing this paved road. And like, why is this valuable? It's valuable because it allows us as an organization to kind of invest in separating the concerns. We want to make sure that those stream-aligned teams can continue to move really quickly, and we want them to not have to think about infrastructure and platform-related issues. We want them to be focused entirely on their domain problem. So by providing us common platform, it's a way of reducing the cognitive load on those teams by very explicitly giving them less decisions to make, right? Bounding their decisions through a set of constraints that we provide through the platform, and those set of constraints actually free the stream-aligned teams to be able to, spend their time thinking about the domain rather than thinking about stuff that's, in the Amazon term, undifferentiated heavy lifting. And what I've observed is that large-scale organizations, the eBays, the Googles, the Netflixes, the Amazons of the world, actually often invest more than 50% of their engineering investment in these platform capabilities. And that might seem strange to people, but if you think about it, at large scale, investing in the platform where we invest in one team that enables 5 teams or 10 teams or 50 teams or 100 teams, like those common investments actually become more and more valuable as we get larger in scale, if that makes sense, right? So there's a larger return on investment from investing in those platform capabilities when you get to large scale. So this is a pretty interesting thing that I've seen grow up over time. So let's talk about some other aspects of architecture here. So let's talk about how services interact with each other. So this won't be super unfamiliar to people at a conference like Build Stuff, but it's critical that services in these large-scale organizations interact in an event-driven way. And this is true from a kind of agility perspective, but also from an architecture perspective, right? So what do I mean when I say event-driven? I mean that as we're making changes in one of the services, those state changes are getting communicated outside through a stream of events, typically through some event bus. And an event is just simply a statement that something interesting occurred, and ideally represents some kind of semantic domain event in our domain. And this is valuable because it's decoupling the domains and teams on both sides of that event, right? So there's a well-defined interface around the event. It allows those domains and teams to be asynchronous from one another. And actually, interestingly, it simplifies the component implementation of both the producer of the event and the consumer of the event, right? So if as a service provider or a service implementer, my mental model is that I receive an event, I do some processing, and then I produce an event, that's a pretty simple and pretty straightforward kind of mental model for me to work under. And again, it makes it a lot easier for me to build my component in a reasonable way. The other idea here is storing things internally in the form of an immutable log. So when it's possible, rather than storing state as like individual kind of just records in a database that we update directly, rather we should store our state as an immutable log of events. So we just accumulate the set of events that we've received, and we use that to manage our state. Then again, this is not going to be unfamiliar to people at Build Stuff, but this is essentially event sourcing. And interestingly, an event source model built on an immutable log often actually also matches our domain problem really directly. So when I was at Stitch Fix, which is a clothing retailer in the United States, we could have remembered the state. We'd sent out packages to people through the mail, and we could have just had a record in the database that said, what's the current state of the package? But oftentimes we really do want to know the kind of history of that package. When did we pack it? When did we pick it? When did we pack it? When did we ship it? How, where is it along the carrier route from us to our customer? So it's really important for us. It was really important for us from a domain perspective to remember all the individual steps in that kind of workflow. And again, just like the other architectural aspects, this log idea also encapsulates a bunch of architecturalities, right? It encapsulates the durability. It encapsulates our ability to be traceable and auditable. When we store these logs, it allows us to replay those logs later, either when there's an issue or if we ever want to test something. And then also from a kind of like comprehensibility and cognitive load perspective, having our state, stored in this immutable log makes it really explicit and really comprehensible for developers to figure out what's actually going on in the system. And then in case anybody was worried that, if we just continue to, accumulate logs ad infinitum, that would be a problem, the standard technique here is that we would collapse, every so often we would collapse the log into snapshots for efficient storage. Okay, and so the other idea here when we combine those several ideas is we want to, as the component builders, we want to embrace the asynchronous nature of the interactions, right? We want to decouple the operations from, service A that produces an event from service B that consumes the event. Decouple those operations in time. And it allows us to decouple the availability of those two systems, right? So A can be up or up or down, B can be up or down. They can still move independently. They can be scaled independently. It actually allows more complex processing on the consumer side, more time-consuming stuff than we'd be willing to do when an actual user is waiting. And then interestingly, because this asynchronous, because this connection between these two things are asynchronous, it's safer from a development perspective for us to be able to make independent changes on the two sides. And interestingly, just like from the event-driven perspective, it actually simplifies the component implementation where we don't have to worry about things being synchronous. So an interesting, corollary or an interesting kind of architectural power that this gives us, which we're going to explore, at the end of this talk, is the ability to invert our overall kind of workflow, overall architecture from a call graph of synchronous, A calling B, calling C, calling D in a synchronous way, and invert that to something where we might think of it as more of an asynchronous workflow, where, D produces an event which is consumed by C, produces an event which is consumed by B produces an event that's consumed by A. And when this is possible in your domain, and it's a lot more possible than I think a lot of time people think, is where it actually can be orders of magnitude simpler to implement and orders of magnitude less resource intensive. We're going to explore this at the end of the talk with an extended example from Walmart, actually. Okay. So the other idea I want to talk about here is decomposing changes into incremental units. So every time we think we have a really large change to do, kind of back to the iterative development that we were talking about earlier, we want to decompose that large change into smaller incremental steps that allow us to make those iterative steps quickly. Each of those steps is going to maintain forward and backward compatibility, so we can move forward and move back in a safe way. And then as a consequence, in one of these large scale systems, it actually means that we often have multiple service versions coexisting at the same time. So those transitional states between, part of the system is on version 10, another part of the system is on version 11, those actually are normal. Those are kind of the common case rather than the exceptional case. The other idea here is making sure that we're getting fast feedback at all levels of the system. So from my perspective, if there's kind of one investment that I can make in a system when I would come in as a leader, it's almost always more testing. And why do I say that? It's actually not because I want to slow things down and do more work. It's actually because tests, in my experience, help us to actually go faster. Right. So tests are, solid ground underneath our feet. I'm a runner, and when I go running, the faster I can go faster when I'm on solid ground instead of on, sand or something like that. So, it actually being on solid ground actually allows us to move much more quickly. Tests help us obviously to make better code because it gives us the confidence as we're going through and iterating. It gives us the confidence to break things and to do some risky refactors. It's not so risky if we have tests to catch our problems. And tests also help us to make better systems because it allows us to catch bugs earlier and it allows us to fail faster. But I think less well appreciated and maybe even more important than any of those other ideas is that tests actually help us to make better designs. So when we have testable code, what does it mean to have testable code? It means that that code is modular. It means it has good separation of concerns, and it means it encapsulates different components from each other. Well, that's just, what I just described there is good software engineering. So by building in tests from the beginning, it actually it's a good forcing function for us to build and implement better designs in our software. But don't take my word for it. Michael Feathers, who's the author of one of my favorite books called Working Effectively with Legacy Code, says this. He says, there's a deep synergy between testability and good design. All of the pain that we feel when writing unit tests points at underlying design problems. So, the earlier that we can do that we can have that feedback from the tests, the better, because it allows us to then improve our design and find and fix those underlying design problems earlier in our development lifecycle. And so what would it be like if we implemented things in this kind of test-driven development approach from the beginning? Well, I had this experience. So when I was working as the engineering leader at Stitch Fix, they had a long-standing approach with a test-driven development oriented approach. And, as a consequence, we basically had no, global bug tracking system. I mean, we produced bugs, like we were just as fallible as anybody. And to be honest, we didn't have magical developers. We had very average ones. But it was the test-driven development practices that actually made those kind of average developers produce outsized, amazing outcomes. So we essentially had what I would call inbox zero for bugs. So, as we found bugs, we would just fix them because we didn't have this big, long backlog of, hundreds and thousands of bugs that we knew about weren't planning on fixing. And then when we had a backlog in our system, the backlog was, new features that we wanted to build, and then technical debt that we intentionally took and we want to repay. So this is what one could have if we actually, really build systems and from a test-driven development approach. It's amazingly powerful and makes teams 5x to 10x more productive than other ways that I've ever seen. Okay. So the last kind of feedback that I want to talk about here is from a continuous delivery perspective. So, we want to make sure that at least we have the ability, whether we decide to do it or not from a business perspective, but we have the ability to deploy our services and applications really rapidly. And so, all the tools that we have in 2022 will help with this. So we want to have a really robust build, test, and deploy pipeline, which definitively tells us whether the software is ready to go. We want to have a canary deployment capability that we can try things out in one part of the system and then roll it back if it doesn't work. We want to make sure that we're leveraging feature flags to turn things on and off for individual customers. We maybe want to leverage dark launches if we have something that's potentially performance sensitive. We can launch it without actually showing it to people. We want to be monitoring our service level objectives, and again, rolling things back if our service level objectives are at risk. And then potentially we want to be sending synthetic tests to monitor whether the system is doing well. And if we do this, we end up with a lot more solid systems, right? This is a kind of agile, but also architectural approach where we're able to release smaller and simpler units of work, which gives us the ability to release smaller changes that are, easier to roll back and roll forward. They fit in our heads, so, they're faster to fix, they're easier to understand, and they're simpler to diagnose when they go wrong. And actually, as a consequence, it allows us to speed up the rate of change that we have, and at the same time reduce the risk of change that we're incurring. So I want to briefly talk about the work that I've been doing over the last 2 years at eBay. So I was the leader of a cross-company initiative, which we called the Velocity Initiative. And the idea here was essentially to implement continuous delivery practices across the company. So, and our general idea was, iteratively identifying and removing bottlenecks for teams. So the question that we would always ask with the individual teams we were working with was, I see that you're deploying, once a week or once every 2 weeks for this particular application that you have. What would it take to deploy your application every day? Tell me all the reasons why you couldn't deploy every day. And so they would give us a big, long list of things that, they would want to do. Builds take too long and the pipeline doesn't work and my tests are flaky and we don't have an automated deployment capability and we don't have a canary capability, et cetera, et cetera. And, because I was also leading the platform organization, I could say to them, great, you just gave me our team's backlog. And as a consequence, I talked about this in more detail at Build Stuff last year, but as a consequence, we were actually able to double the engineering productivity of the teams that we worked with. So I felt pretty good about that. And when I say doubling engineering productivity, what do I mean? I mean that, before we started doing this work with an individual team, they'd be releasing features and bug fixes on a certain cadence. So in a given time, they'd be able to release a certain number of features and bug fixes. And then after we did this work, they were able to release twice the number of features and bug fixes in that same time with the same, team and the same composition, et cetera. We also were able to move the accelerator, the DORA metrics pretty substantially. So, we improved the deployment frequency and the lead time by 5x for the teams. And even though we weren't really focusing on the quality side of things, we actually also substantially improved the quality, exactly as all the state of DevOps research would have predicted. We actually were able to reduce the change failure rate and to reduce the mean time to restore by 3x. And how does this relate to architecture? Well, it turns out that, when I came into eBay and I wanted to make a bunch of changes to the architecture, it turned out that the prerequisite for us to be able to make those large-scale changes to the system was actually our ability to deliver very quickly and rapidly and safely smaller units of work. So this investment in continuous delivery was actually an investment and a prerequisite for making larger scale architecture changes to the system. Great. Okay. So we talked about business and customer value. We talked about fast, sustainable flows of change. And now I want to talk in our last section about long-term evolution of our software and our system. So first, I want to talk about making sure that we're designing things in an 80-20 perspective. I want to talk about how services evolve in these large-scale service ecosystems. And then lastly, I want to talk about evolving architecture. So first, why do we even evolve our systems at all? I mean, why didn't we, get it right the first time? Well, it turns out that, things change over time, and, our constraints and capabilities from an organization perspective change. We're in a different situation when we have 1,000 users versus when we have 1 million or 1 billion users. Turns out the problem evolves over time, right? The competitive landscape is changing, market conditions are changing, and also, frankly, our understanding of our domain changes over time. And also, our solution evolves, right? So the domain decomposition that we started with is often not what we end up with, and then clearly over time, technology landscape is changing, and the standard approaches are changing over time. So, as my friend Dave Thomas likes to say, big design up front is dumb, but no design up front is dumber. So we've tried both those things, right? In the old days, we would try big design up front and 1,000-page specs that people would type. That definitely didn't work. But also, there's a lot of people, I think, even still that think agile means you're not supposed to design or think up front, and that's ridiculous. So the way to think about it really is an 80-20 rule, as with almost every kind of situation where we're in this trade-off, right? We want to do a minimal design that gets us started. We want to be doing pilots and prototypes of new ideas. And then we want to rapidly adapt based on real world feedback. We want to make sure that we get our systems out to customers as soon as we possibly can, so we can get actual real world feedback from the business and customers as soon as we possibly can, so that we can then adjust our design and adjust our implementation. So in these large scale, high performing organizations, these service ecosystems evolve really substantially, right? So at Google, for example, when I was there, the situation was a lot like biological evolution. So there was variation and natural selection. New services were being created all the time. Services, as they continued to be used, would continue to be invested in. And as soon as services were kind of superseded by something else, those services we deprecated. And then, as I was talking about in terms of the domain evolution, domains are over time growing and dividing. And the mental model I like to have is cellular mitosis, where, a domain starts as one unit and then divides into two, and then maybe those divide into two, et cetera. And the sort of, internal Google joke was that, there was so much churn in services within Google that it felt like every service at Google was either deprecated or not ready yet. Okay, so now I want to talk about, as I mentioned, I want to talk about an example, an extended example from Walmart where they applied a bunch of these principles and really made some amazing improvements. So all this information comes from an excellent presentation from Scott Havens, who worked at Walmart at the time back in 2019. The domain was what's called item availability. So, when somebody goes to the Walmart website and they put something in their cart, is it possible for Walmart to ship that thing to them, within a reasonable time? So is this item available to ship to this customer? And the customer level kind of service level objective was 99.98% uptime, and they wanted to get back to the customer within 300 milliseconds. And as you can imagine, at some place as large as Walmart, there was a ton of complex logic that involved lots of different teams and lots of different domains about trying to figure out where items were in the vast Walmart network, what other kind of claims on those items might exist, and how could it get to the user. And the original synchronous architecture, and I'm going to show you a diagram on the next slide, was a 23 nested synchronous service calls, all of which were in the hot path, a failure of any one of which would invalidate the results. And if you do the kind of SLO availability math, each one of those services needed to have 5 nines of availability and had a budget of 50 milliseconds of marginal latency. So that kind of system, it was extremely expensive to build and operate. And like the details here aren't super important, but just look at all the red. Like that's the hot path of, when somebody comes to walmart.com and tries to see if they could buy a particular item. So this is a pretty rickety, situation, and there was lots of monetary and people investment in all of this. So instead, what they did is, using a bunch of the kind of event-driven principles that we were talking about, they inverted each of those services to, instead of taking synchronous calls kind of top down, to use asynchronous events more in a event-driven workflow from the bottom up. So each of those services would, receive events from their dependencies. They would be storing those events in an immutable log, as we talked about. They would maintain a materialized view of that data, so they could offer a kind of consistent view to the next level up. And again, I'll show a diagram on the next slide. But after they did this asynchronous re-architecture, there were only 2 services in the synchronous hot path. Most of those asynchronous service SLOs were able to only need 3 nines of availability. And sometimes the latency you could expect from them was seconds or minutes, because, inventory things in the physical warehouses aren't changing, microsecond by microsecond. There was way more resilient to delays and outages, and it was actually orders of magnitude simpler to build and operate. So this is what the architecture looked like after they finished this, right? So on the right-hand side, you can see the synchronous hot path is just those two synchronous calls, really simple, really straightforward to scale and operate. And then all of the collection of the item availability information, all the kind of rules and state that went into that was all accumulated in this kind of asynchronous event-driven workflow, going kind of left to right. Okay, so we made it. So we talked about business and customer value. We talked about fast, sustainable flow of change, and we talked about long-term evolution. And again, as I think you can see, agility and architecture work hand in hand together, right? So an agile approach needs a solid architecture underneath. A solid architecture is maintained and kind of evolved through an agile methodology. And, in all cases, we have the situation of constant change, iterative steps, and then a prioritization of fast feedback. Okay, so thank you very much. I think we might have time for a couple of questions.
No, if not, then there's a question that I would like to put to you for those people that are unfamiliar with the term. Could you maybe talk a little bit about SLO versus SLA?
Sure, yeah. So an SLA is a service level, well, let me do it the other way. A service level objective, SLO, is what we want out of the system. An SLA, a service level agreement, is what happens if we violate an SLO. That agreement is some contract that we make maybe with ourselves or maybe with external customers about, okay, if we violate this service level objective, we're going to pay you money, or you're going to, get a discount next time or something like that. So that's the difference between an SLO and an SLA. An SLA is an SLO with teeth.
I love that description, an SLO with teeth. And a last one, because I think we've got enough time for one other question that I was putting down here. Your first slide, you say what you have, being agile is a requirement for having good architecture. Having good architecture is a requirement for being agile. In your experience, which side of the circle does this generally start?
I mean, the honest answer is I think you have to start on both sides. That's kind of the point, I think, is that we need to come into our organization, or start our project or whatever by building out a solid architecture. It's small at the beginning, but then always having that iterative approach to building stuff. Like, I don't think an effective engineering organization has one without the other. Okay.
Awesome. Well, we're about on time, so I would like to thank you very much again for your time today, for a really good session. You can't see it because you're in a different part of the world to me, but I have a list of notes to take back to my job next week when I return to the Netherlands. So thank you so much, and have a good day further.
Great. Thank you.
And I believe that we have a 20-minute break now, so there's time for snacks and energy and hydration. So enjoy all, and we'll see you at the next session. Thank you. That was a really awesome talk. Thank you so much.
Oh, thank you.